Okay, this is the last major part of this section. It's on non-homogeneous systems. A system of equations is called non-homogeneous if it has this form, ax equals b, where b is not the zero vector. And that's written as a matrix equation. If you wrote it as an augmented matrix, it would look like this, where somewhere over here you had at least one thing that wasn't a zero. And the solutions to a non-homogeneous system don't form a vector space. Instead, they form a translative vector space, and sometimes that's called an affine space. What I mean by translation is, like let's say in R2, this would be a subspace here, this line that goes through the origin. If you took that line and shifted it off of the origin somehow, and this is supposed to be parallel to it, if you shifted it off, that would be like that's no longer a vector space, but it is a translate of a vector space there. And if you think about it, if you had a basis of this, if you wanted to get all the points on this line, really what you could do is take any point on here and then add a single vector. Let's say we added this vector here. That would move something from the green line onto the other line. So this little arrow I put across here, that's what's called a particular solution. And if we think of it just as a point, it's a point on here. So the idea is, if you take a solution to the homogeneous system and you add any particular solution to the non-homogeneous, then you get the solution set for the non-homogeneous system. So I want to do several examples here. The first one is a fairly typical example. And let's see. I want to do this example, and then we've got several more of varying levels of difficulty. But let's do this first one just to sort of get the technique down. Now, to start with, it's not really any different than solving this system like we've already been doing. It's really just how we write the answer that's going to be different this time. So let's take this matrix, and I've got it entered into Octave already. Let's see, that's it. Now I'm going to be a little bit lazy here, and I'm just going to say RREF, and I'm going to write the reduced row echelon form here. Yeah, that's a system, and it's not a matrix, but we know what it means. We're taking that system, writing it as this matrix that I've got on Octave down here, and when we row reduce it, we get this. So let's see, that row reduces to 10407. Next line is 0, 1, negative 2, 0, 2, and 0, 0, 0, 1, 0. That's a star there, but it means if we were looking at this in a different, if we're looking at it in short form or float form or whatever, it would be a 0, but it would be, the computer has some round off error. So anyway, that's what it row reduces to. Now we've got X, Y, Z, and W. I'm going to circle my leading ones and point out my free variable. So let's write this as a general solution. We're going to get X is equal to 7 minus 4Z. Y is 2 plus 2Z. Z is a free variable, so Z is just Z. And W is 0. Now I'm going to come back in here and write in a little bit of extra stuff. I'm going to write those in. And that's our solution to the system. I'm going to move it off of this because I don't like it sitting here on the split between two pages. So that's the original system. Or I'm sorry, that's the solution to the system. But what we're going to do is write it as XY ZW equals, I'm going to pull this out, 7200 plus z times -4, 2, 1, 0. So that's the only real difference, is how we're writing this solution. And I want to label this. This bit right here is my particular solution. That's one particular solution to the system. This over here, z times this is a solution to the associated homogeneous system. What that means is, if we went back up here to the original and took these constants over here, if we took those and replaced them with 0, 0, 0, then this would be the solution to it. So if you think about what this is in, we've got four variables here, so this is in 4-dimensional space. This is a line through the origin. If we just look at the homogeneous system, the homogeneous solution, that's a line through the origin, and this is what it's offset by. So if we wanted to describe this geometrically, this is a line, as in 1 dimension, in R4 through the point (7, 2, 0, 0). And that's how we describe it geometrically. Now, what I'd like to do is, I want to go ahead and do the next example. This next example is easier to visualize, and I want to write it out in the same way. If you look at this, this is a system of 2 equations in R2. But if you look at them closely, you can see they're really the same equation. 3x minus 2y equals 2. And if you multiply that by 2, you get the second equation. So let's row reduce that. If I put that into octave, I mean, this one is simple. I could do it by hand, but I'm not going to. We get 3 minus 2, 2. 0. No, not a 0. 3 minus 2, 2. 6 minus 4, 4. And when we row reduce it, we get that. So we get 1 minus 2/3 and 2/3. And zeros. All right, so I didn't leave myself much room. I'll label these below. This is x and this is y. That's leading 1, and y is free. So I'm going to write my solution as x is equal to 2/3 plus 2/3 y. And y is a free variable, so it's just equal to 1y. So if you take this and write it out, you get xy is equal to 2/3 1, or no, 2/3 0 plus 2/3 1 times y. So this is my solution, and this is my particular solution to the non-homogeneous version, and this is the solution to the homogeneous version. Now, if you think about what this is really just, I mean, this is a lot of work for a line. This is this over here. If you take 2/3 and 1 and multiply it by anything, what you've got there is just the line that goes through the origin. Let's see. 2/3 and 1, so that's like the point 2/3 1. So go over 2/3 and up 1, and you've got this. That's this vector here. The point 2/3 0 is here-ish. So what we're doing is we're taking that line that's spanned by the black vector, and we're just going to translate it over to here. That gives us this line. That line is the solution set here. It's not a subspace. It's a subspace that's been translated by some amount. It's been translated by this amount. All right, so I want to do some more examples, but we'll save them for the next video because this